All right, we're continuing on what we learned yesterday. This time, though, we're going to look at it from an algebraic perspective. We're still solving systems of equations, so we're still finding where two systems will, or two equations, I should say, will meet and intersect. But we're going to do this algebraically today, with the exception of the first question, of course, where we're going to review. So again, we're going to have a quick recap of solving by graphing. That's what we did last class. Then we'll talk about solving algebraically by substitution and solving algebraically by elimination. Just like last class, this is mostly a review of what you guys would have done back in Math 10C. So it's not going to be super new, but it's probably been a while since you've thought about it. So it might feel new is what I'm saying. All right, anyway, let's get going. So graphing example, same kind of thing we did yesterday. Solve the following system of equations by graphing by hand, round the solution or solutions to the nearest hundredth. I don't know why it says that, because you're not going to need to do that. These are going to be whole number solutions, or integer solutions, I should say. Anyway, first things first, I would graph this linear equation first, because linear equations are way easier to graph than quadratics. A linear equation can be graphed just by looking at your y-intercept, which is the constant term, so +1, and then looking at the slope, which in this case is -1, which means I'll go over 1, down 1, over 1, down 1, and so on. It'll kind of just follow this pattern here. There we go. You won't have to draw nearly as many dots, but believe me, I'm doing this because without a ruler, it becomes really tough. Anyway, let's go. Oh no, I'm getting a little off. That's okay. That's okay. Do what we can do. Do what we can do. That's all I can do. Anyway, there we go. All right, that's, pretty pitiful, but you know what? I'll say that works. Anyway, so next up, we'll graph this quadratic. Remember, graphing a quadratic involves finding the vertex first. The vertex is going to be found by saying x equals -b over 2a. In this case, that's going to be -6 over 2 times -1. So -6 divided by -2, that's going to be +3. And then you plug that number into the equation itself to solve for it. So -3 squared, so that's going to be -9. Plus 6 times 3, so plus 18. That's going to bring us up to +9. +9 minus 5, that's going to be 4. So then that means our vertex is the coordinate 3, 4. So 3, 4 looks like it's going to be way over here, not even remotely close to this other graph, and that's okay. But what we should do next is we should use our 149 rule. So after here, it's 149 rule. 149 rule says start at your vertex, go over 1, and then up 1 times a. Well, 1 times a is 1 times -1, so we're going to go up -1. Or in other words, we're just going to go down 1, right? So we're going to go down 1. There we go. Go back to your vertex, go over 2 points, and then up 4 times a. Well, 4 times -1 is -4, so we're going to go down 4. There we are there. Then you go back to your vertex, go over 3 points, and then up 9 times a. Well, 9 times -1 is -9, so we're going to go all the way down here. Ooh, and what do you know? Down here at -5, it looks like we're intersecting with our graph. From there, let's just make this symmetrical on both sides. Something kind of wonky is going to happen there. I wonder what's going on. Oh, there. Never mind. My eyes were deceiving me. I was going to say it has to go over here. What on earth's going on? But no, it has to go right here. My eyes were deceiving me. Sorry, I was going to say something weird's happening there. I thought we were going to end up with a decimal answer. Anyway, I just goofed. Not a big deal. All right, so that is more or less okay. Let's try connecting our dots now as best as we reasonably can do. And I'm just going to say forget it. There we go. Good enough. Good enough. There we go. That was absolutely miserable. But you know what? I'm not an artist. I'm just a math teacher. Anyway, from here, we can actually see our solutions. We got a solution right there, and we got a solution right there. The coordinates of these solutions are going to be 1, 0. So 1, 0 is one of our solutions. And then the other solution is 6, -5. And if you really wanted to, you could verify these solutions by plugging them both in and seeing if it gives you the same answer for both. But I don't really care to do that. So you know what? I'm going to skip that. We don't have to worry about it. And it didn't even ask for it anyway. It didn't even say verify. Whew. Look at us go. Awesome. All right. So main focus for today is solving systems of equations algebraically. Solving by graphing apparently isn't enough for us. We have to know how to do this by hand as well. So another important skill is to be able to solve systems algebraically without using a graphing calculator. In Math 10C, you would have covered 2 ways of doing this: substitution and elimination. Nothing changes in Math 20-1. Those are still our 2 ways of doing this. This is the same stuff all over again. It's just this time around, we might end up throwing some quadratics at you, and that's kind of a hassle. In your notebook, that I left like a solid like inch of space underneath this. I don't know why I did that. Draw a picture, smiley face. Do something better than that. Make it a person. Give him a hat. Anyway, let's move on. So substitution is the first way we're going to cover. So solving by substitution requires step one, get one of the variables, either x or y, all by itself. It doesn't matter which one you do. You just have to get the variable all by itself. That includes any x squareds, that includes any x cubes, whatever. You have to get all of that by itself. 99% of the time, that means y by itself is probably going to be the way to go. But you actually have flexibility and freedom in this. It's really up to you. Step two, take what that variable was equal to. So like y equals blah, blah, blah. Take that blah, blah, blah and substitute that for any time you see your variable in the other equation. So in the other equation, every time you see a y, replace it in brackets with whatever y was equal to, right? Step three, solve for your variable. In doing so, you shouldn't have two variables in your thing anymore. You should be able to solve for whatever that variable left over is. And then once you get that other variable, use it to find your other one. So plug it back into the y equals thing, bingo, bango, bongo, you're good to go, right? No big deal. This is way easier to understand when you see an actual example. So let's do one. Solve by substitution. 2x minus y equals 15 and 3x plus 2y equals 40. You've got some freedom on this one. It really doesn't matter which one you do to get your variable all by itself. But I think the one that's kind of just begging us to get the variable by itself is getting y by itself over here. We could get y by itself if we just add y over to the other side and then minus 15 back over. So in other words, we could say y equals 2x minus 15. That was pretty straightforward. That was a pretty clear way of getting the single variable by itself. Take what that variable was equal to now and substitute it into the other equation for every time you see that other variable. So every time we see y in this other equation, change it out for 2x minus 15. The good news is we only see it the one time. So it's not going to be a huge amount of work here. This is just going to become 3x plus 2, and then whoop, not allowed to say y. I got to change that with 2x minus 15. Notice I use brackets because I'm replacing y with this whole chunk. So it's 2 times this whole chunk. Really important we do that. And that's equal to 40. Let's clean this up now. This 2 can double dip its way through here. So we're going to have 3x plus 4x minus 2 times 15 is minus 30 equals 40. Now we can combine our like terms. 3x plus 4x is, of course, 7x. Let's add 30 to the other side, too, while we're at it. So that'll make 7x equals 70. And then just divide by 7 on both sides. And you're going to see that x is equal to 10. There we are. We just solved for x. But that's not enough here. We now have to solve for y. But the good news is with substitution, honestly, you're going to find them kind of like biased. I love substitution. I think this is the better way of doing it. That's why I always teach it first. But anyway, x equals 10. We plug that back into y equals 2x minus 15. That gives us y, right? Because y is all by itself already. Whew, couldn't have been nicer. Look at that. So this is y equals 2 times 10 minus 15. Well, that's just going to be 20 minus 15, which of course means y equals 5. And if you were ever doubting any of this, you could have just plugged x and y, so 10 and 5, into both of these expressions, and you're going to see that it gives you the same thing, right? Because 2 times 10, 20, 20 minus 5, yeah, that's 15, so that worked there. And then same with over here, 3 times 10 is 30, plus 2 times 5 is 10, 30 plus 10 is 40, right? So it worked. Substitution, that's all there is to it. Get one of your variables by itself, go from there. All right, we're going to have another look at an example. That was like a Math 10C example. Here's more of a Math 20-1 example. Oh, Nelly, look at that. We got a quadratic. Oh, boy. Okay, so when you have a quadratic, the heat kind of turns up a little bit here. Now, just looking at my notes right now, I'm not sure why I did it this way, because remember, the first step of solving by substitution is to get one of your variables all by itself. Looking at this again, I think it's pretty obvious. Y is all by itself right here. So it's like it already is by itself. So we could just take this and plug it in here for anytime we see y. For whatever reason, though, I didn't do that. What I did in my notes is one extra step, and I'll just follow it through anyway, but I guess this will just show you it really doesn't matter. I got y all by itself over here for some reason. So I went y equals 1 minus x. And then I used that to substitute it over here. So I replaced any y that showed up in this equation with 1 minus x. Really wasn't a big deal. It's really all the same thing. So 1 minus x equals x squared plus 3x minus 4. This is clearly a quadratic equation because there's an x squared going on. And to solve a quadratic equation, we always had to make it equal to 0. So let's minus 1 from both sides and then add x. And that's going to give us 0 equals x squared. And we had to add x, so it's plus 4x. And we had to minus 1, so that'll be minus 5. And then, of course, to solve a quadratic, this is a kind of a callback to our quadratics unit. As long as that quadratic's equal to 0, you can just factor it and then find the solutions that way. Factoring this quadratic just means we're going to have to use the regular old sum product rule. So we're looking for two numbers here with a sum of 4 and a product of -5. Well, I think those two numbers are going to be positive 5 and negative 1. So we'll write that out. 0 equals x plus 5 times x minus 1. And then the solutions to this are going to be x equals -5. That's for this first piece. And x equals positive 1. That's for that second piece. Now, usually I'd write them left and right of each other, but I was just thinking, just because I have room here, I'm going to write them above and below each other for good reason. These are two separate solutions. They're both x's. One single coordinate can't occupy two different x's. That doesn't make any sense. So we are going to actually have two solutions for this. With the solution x equals -5, it has to correspond with some other y value. Because ultimately, if we were going to graph this, we're looking for the two of these, and I don't know what the functions look like. Maybe one looks like this, and maybe the other one looks like this or something. We're looking for where this function, crosses the other one. And again, it is crossing two places, so really it'll look more truthfully kind of like that. But again, we want to find where this crosses in two different places. So what I'm getting at here is we need to find the corresponding y value to each of these x's. If x was -5, we'd have to plug that into here to find what y would be equal to. So when x is -5, y equals 1 minus -5, which means y equals 6. Okay? What that really means, what I'm trying to spit out here, is yes, x is equal to -5, but with that coordinate, y would equal 6. So maybe it's a good idea for us to actually write out that coordinate. Our answer, as one of our solutions, would be the coordinate -5, positive 6. That makes it a little bit more clear, right? It's not that this -5 can like go with any y. It has to go with that y is equal to 6. Same with this one. When x is equal to 1, we would have y equals 1 minus 1. So that means y would equal 0. So again, it's probably better to communicate this as the coordinate 1, 0. That would be your other solution to this system of equations. You know, my graph that I drew, that was actually somewhat accurate, actually. You know, I was just like, freehand drawing that, but whatever, you can kind of get the idea. Still, that's the idea. So again, we want to make sure that we find an x and its corresponding y. And I go back to the last example I did. I didn't list it as a coordinate, but since there was only one x, there must have only been one y. So if we want to like kind of make this all consistent, we could have written this as the coordinate 10, 5, right? I didn't worry about it in that last question though, because again, there was only one x. So that one y that goes with it has to go with it. It's not going anywhere else. Anyway, let's move on now to elimination. So elimination is another strategy that allows us to solve systems of equations. There are certain situations where elimination is actually better suited. So even though earlier I said I prefer substitution, there are some times where elimination just straight up works better. So to solve by elimination, there's a little bit more background work you have to do most of the time. You need to rearrange both of your equations so that all of your x's line up and your y's line up and any of your numbers line up as well. So in other words, you have to rearrange your equations so that they're in the same general quote unquote order, okay? Then you actually literally write your two equations one over each other. So they're completely lined up. Your x's are all in a column, your y's are all in a column, your numbers are all in a column. If you have an x squared, those are all in a column as well. Then what you do is you can multiply one or both of the equations by a whole number so that one of your variables have matching coefficients. That probably sounds like total French, but the idea here is we're building up to step 3, where we are adding or subtracting the two equations together to eliminate the variable, right? So the whole idea here is you basically just like figure out how many of one of your equations you'd need, to totally eliminate one of your variables, knock it out of the park, and then you just solve for the leftover variable. As always, this is way easier to see with an example. It really sucks just explaining it. So let's see this first example here. We'll do two examples of this. This is more of a Math 10C level example, solved by elimination. So first of all, we can see that both of these equations have a certain number of x's, a constant number, and y's, but they're just kind of in different orders. Just for the sake of consistency, I kind of like this order better on this one. There's no real reason why, I just do. So I want to rewrite this one on the left so that it's some number of x's and then some number of y's and then an equal sign and then my constant term. To do that, I just have to add 2y to both sides. So now I can rewrite this as 3x plus 2y equals 19. So again, what I did there was I just made sure I had some number of x's and then some number of y's and then my equal sign and then my constant, just like this one where it's some number of x's, some number of y's, equal sign, constant, right? They got the same flow to them. Then I'll take this and I'll line it up with the other one, right? So we won't worry about this line anymore. That thing's dead. But this is now 10x minus 4y equals 10. So we've lined them up now. Now here's the question. Looking at your variables, is there some number we could multiply one of these two equations by that would allow us to perfectly match both of our variables? Now, by perfectly match, they don't have to have the same sign in front of them. They just have to be the same value. Well, here's what I could do. I know that I could take this 2y and multiply it by 2 to turn it into 4y. So why don't we just take this top equation and multiply it by 2? What that's going to do is it's going to give us 6x plus 4y equals 38. Now we're allowed to do this because really all we've done is we've multiplied both sides of the equation by 2. So we've just scaled it up, right? We haven't changed what the x's and y's are equal to. We've just multiplied both sides of this equation by 2. So we've just made it bigger without actually affecting the ratio of all of our parts. So I'm going to say that this thing is dead here now too. So we've got these two equations to work with. This was our original right-hand one, and this is the original left-hand one. Now I want you to notice that between these two equations, we could cancel out these two terms if we just added these two equations together. Negative 4y plus positive 4y would equal 0y. Those would totally cancel out. If this was, let's say, a minus 4y and a minus 4y, then we would have to subtract the two equations because subtracting two of the same thing will eliminate them. But because these are opposite, negative and positive, we can just add these two things together and then we're good to go. So what that would give us is 10x plus 6x, so that's 16x. Negative 4y plus positive 4y is just 0y, so I won't even write it. And then 10 plus 38 is 48. So we're just left with now 16x equals 48. Then, of course, to get x by itself, just divide both sides of this single equation by 16, and you're going to find that x is equal to 3. Since we've now found x, we just need to plug it into either one of our equations, really, and solve for y. I think the one I used was this guy over here. So I could say 3 times 3, because it's 3x, so 3 times 3, equals 19 minus 2y. Well, that's going to be 12, or sorry, not 12. What am I doing? 3 times 3 is 9. 9 equals 19 minus 2y. Let's minus 19 over. That gives me negative 10 equals negative 2y. Divide by negative 2, and we have y is equal to positive 5. So in other words, through a very roundabout method, we were able to solve for an x and y that actually satisfies this system of equations. And if you don't believe me, you could always plug x is 3 and y is 5 into each of these, and you're going to see that they are, in fact, going to work. You might see right now why I don't like elimination so much. Others, you might look at this and go, hey, you know what? I actually prefer this. It's just a matter of lining things up and canceling things out. You know, really, I guess it's all a matter of opinion, but whatever. Let's see a more complex example here. We have a quadratic and a linear equation, and we want to solve this by elimination. Here's what's kind of cool, though. It's kind of already lined up in a way. This has a y, an equal sign, a certain number of x squareds, a certain number of x's, and then a constant. This has a y, an equal sign, some number of x's, and then a constant. So it's almost like we could rewrite this as y equals 0x squared plus 12x minus 1, and now it has the same kind of flow as this guy. Well, let's do that. Let's just write this underneath it now. Y equals 0x squared plus 12x minus 1. Now, the question is, we want to eliminate one of our variables. So we want to make sure that the coefficients in front of one of our variables are the same. I think the absolute easiest way of doing that is just accepting it as it is right now. Our y already has the same coefficient. It's just one y on each of these. So we have to figure out, are we going to add these two equations together or are we going to subtract them? Well, if you added these two equations together, you'd have 2y here. And that's not what we want. We want to have no y at all. So how about we subtract these two equations? And this is where you got to be kind of careful. Let's deal with it one term at a time. Y minus y is, of course, 0. That's going to equal 3x squared minus 0x squared. That's like minus nothing. Well, that's still just 3x squared. 6x minus positive 12x is actually going to be minus 6x. And then the one you really got to be careful with, negative 10 minus negative 1 is like saying negative 10 plus 1, right? Because it's like a negative 10, we're taking away a negative 1. We're going to be left with, long story short, negative 9. Okay? So 0 equals 3x squared minus 6x minus 9. This becomes like an adapted quadratic, right? Like adapted sum product rule, I should say. However, I actually noticed something else that might make our lives a little bit easier. Notice all of these terms are divisible by 3. You can use the adapted sum product rule here because, again, the a value is a number other than 0 or other than 1. But since we can divide by 3 on all these, let's make our lives easier and let's just do that. This is 0 equals 3 times x squared minus 2x minus 3. And then notice inside the brackets now, after we factored that 3 out, you can just do the normal sum product rule here and figure out your factors, right? Because again, having our factors is going to allow us to find where our zeros are, right? So this will be a sum of negative 2 and a product of negative 3. Well, that'll be negative 3 and positive 1. So 0 equals 3 times x minus 3 times x plus 1. And then that would mean we have solutions x equals positive 3 and x equals, for this one, negative 1. Now, this is kind of like the one we did a few slides ago where we have two different x's as solutions. Remember, x's as solutions need to have a corresponding y go with it. So in other words, now that we found this x, let's plug it into one of our original equations to solve for y. I think it's pretty clear the vastly more easy question or equation to plug x into would be this one right here, the y equals 12x minus 1. So if we swing this x equals 3 over, that's going to give us y equals 12 times 3 minus 1, which of course is y equals 35. So our coordinate as an answer would be the coordinate 3, 35, and that's one of your solutions. Do the same thing with negative 1. That's going to be y equals 12 times negative 1 minus 1. So that'll be negative 12 minus 1. That'll be y is equal to negative 13. So again, write it as a coordinate to really solidify your answer. That's going to give us negative 1, negative 13. Whew, and we made it. We're done. Look at that. Holy smokes. Well done. So here we go. For practice, page 451, questions 3, and then question 4 ACE, and then questions 5 to 8 and 12. You polish those off, you will be a master at this, I promise. Anyway, if you need me, you know how to reach me. Best of luck.